This is Cryptography, Lecture 3. And cryptography is about sending messages securely. Secure means that the person who gets the message can understand it, but anyone who intercepts the transmission can't figure out what the message is. So typically you have two people, Alice and Bob, and they want to communicate. Let's say Alice has a message she wants to send to Bob. So let's say this is Bob. Here's Alice. And there's going to be a certain message. Yes. So Alice sends Bob the message. And the problem is that there's an enemy, or Eve. And Eve can intercept every message Alice sends Bob, and Bob sends Alice. So if the message is attack at dawn, and you don't want Eve to know when you're going to attack, you can't just send the message attack at dawn. You have to encrypt it or encode it. So Alice encrypts or encodes the message M into what is called ciphertext, C. So the message that Alice wants to send Bob is M, but she converts it to some C, and she transmits C to Bob. And Eve, who can overhear, eavesdrop, intercept every message Alice sends to Bob, Alice knows what C is. She intercepts it. But it's encoded, it's encrypted. And Bob decrypts or deciphers C to get M, to get the message. But Eve doesn't know how to do it. At least if Eve doesn't know how to do it, if Eve cannot decrypt, then the crypto system, this message, is secure. And the game in cryptography is to develop, invent, discover secure crypto systems. So there are lots of ways to do this. One ancient crypto system is just to substitute one letter for another. Substitution. So you have the alphabet A, B, C, D, E, and so forth, if you're using the English alphabet. And you just say, okay, well, instead of A, I'll send K. Instead of B, I'll send R. Instead of C, I'll send T. Instead of D, I'll send A, and so forth. So if you wanted to, you had the word bed, and you wanted to encrypt it by this system, B becomes R, A becomes K, and D becomes A. So if you want to, if this is your message, this is the encrypted message, RKA. So you would send this, and the person who's receiving the message knows what the substitution rule is, and then from RKA can work backwards and get BAD. So this is decryption. And Eve can intercept the message, and if she doesn't know the substitution method, she can't decipher it, she can't decrypt it. So the security of this system depends on Alice and Bob. So this is Alice sending this to Bob. Alice and Bob knowing how to encipher and decipher, but Eve doesn't know. Of course, how do Alice and Bob know what the system is? Well, they have to start out by knowing it, or one has to send it to the other. So if Alice sends to Bob a message that says, I'm going to use the following secret code. In this code, every A becomes a K, every B becomes an R, every C becomes a T, and so forth. But if Eve can intercept that message, she knows how to decipher. So this code becomes insecure. And that's a real problem. That's a real problem. So a fundamental problem in cryptography is how you develop a system of encryption, and how do you tell someone how to encrypt in a way that someone who intercepts your message won't know how to decrypt your system. Okay? So there's sort of a general problem, how to transmit an encryption method that does not permit decryption. So you have to think about this a little bit. So here is Bob. Here is Alice. Alice wants to send Bob a message. She has to encrypt it in some way. Bob has to tell Alice how to encrypt. And you have to assume that Eve intercepts this message. So Eve also knows how to encrypt. So Alice encrypts her message, M, converts it to this encryption, ciphertext C, and transmits C to Bob, and Eve intercepts C. Now, Eve knows how to encrypt a message, and with most encryption schemes, she would therefore know how to decrypt the message. Like if your encryption was a substitution cipher, if you know how to substitute to get a plain text into a ciphertext, so you should know these words. Plain text is the message you're starting with, M. Ciphertext is its encryption. So if you know how to turn plain text into ciphertext with something like this substitution scheme, you then know how to turn ciphertext back into plain text. So this ancient method of cryptography, a substitution algorithm, is not very secure. Because if someone learns how to encrypt, they simultaneously learn how to decrypt. Okay? So this is really a very important issue in cryptography to understand. And there was the following unsolved problem, or problem that was unsolved for a long time, which is, can one invent or create what you might call a public key crypto system. In a public key crypto system, Bob tells Alice how to encrypt a message, the plain text. Eve intercepts and knows how to encrypt because she intercepted the message. She knows what to do, but somehow knowing how to encrypt does not tell you how to decrypt. And this was for a long time the holy grail in cryptography. Can you invent a system with this property, that knowing how to encrypt a message does not tell you how to decrypt the message? And there was a beautifully brilliant and simple solution that was found by several people. One was a group at MIT. There were mathematicians Rivest, Shamir, and Edelman. And their initials RSA gave this the name, the RSA crypto system. The trouble in cryptography is if you invent something, you don't really know if you were the first to invent it, because every country in the world has an agency to develop encryption and decryption methods. In the US, it's the National Security Agency. In Britain, forget what it's called. In Russia, everywhere, every country has its agency for cryptography. And if they develop a secret code method, they don't publish it. They want it to be secret. So you have no idea what people in these secret agencies have done. There's no way to tell. But certainly the first group that developed a public key crypto system in the public domain was this group at MIT, Rivest, Shamir, and Edelman. And they patented it and made a lot of money. And it still is in use. If you buy something on Amazon, it's a secure transaction, as far as we know. Why is it secure? Because you see what you want to buy, you give Amazon your credit card, and they charge your credit card. Now, how do they get your credit card number? You type it into your computer, and your computer sends it to Amazon. But there is the following principle in cryptography, which is no transmission is secure. You always assume everything you send out over the internet can be intercepted, or maybe is intercepted and saved by someone somewhere. There's no secure communication. There's no secure transmission over the internet. Everything you send over the internet can be intercepted and read by someone who might want to do something bad with it. So if you send your credit card number to Amazon as a credit card number, anyone can, well, not anyone, but that message can be intercepted, and people know what your credit card is, and they can use it to your disadvantage. So in the Amazon software, there is something downloaded to your computer. When you type in your credit card number, it is encrypted. And what is transmitted over the internet is not your actual credit card number, but the coded form, the encrypted form of it. And there has to be a system where if someone intercepts the message and gets your encrypted credit card number, they are not able to decrypt it, to decipher it, and get your real credit card number. And how is that done? That's done by using this RSA crypto system. It is used basically everywhere because no one has figured out yet how to break it. And this crypto system is based on the following very simple fact in number theory. Suppose I give you two prime numbers, P and Q. You can multiply them and get PQ. So if you're given P and Q, you can multiply them. So let's say here I have P and Q, and I send them, well, I don't send P and Q, I send their product, PQ. And someone intercepts that. This is an intercepted message. So Eve, the spy who's trying to break into your system and see what you're doing, Eve knows PQ, but she needs P and Q. So the problem is to factor PQ to find the two primes, and this is hard. By hard, we mean not that it can't be done in enough time, but it can't be done in a million years with the fastest computers we now have. So it's basically an impossible problem. So this is really an interesting situation. You have, on the one hand, it's possible, given two primes, to multiply them. That's easy. Multiply PQ. Let's just say that's trivial. Any computer can multiply two big numbers really fast. But if you give a computer the product of two numbers, in particular the product of two primes, and you ask the computer to find the primes, it can't do it. Maybe once in a trillion tries it'll be lucky and do it, but can't do it. And that is the basis of this RSA crypto system. So let me explain what it is, and then I'll develop the mathematics to show you how to do it and explain how it works, understand how it works. So here's the problem, or here's this story. Here's what we have to do. Here's Bob. Here's Alice. And up here, lurking, is Eve. And any message going back and forth, Eve can steal. Eve knows everything Bob sends to Alice and everything Alice sends to Bob. So the question is, so Bob must send an encryption method to Alice. This is what is called a public key crypto system. In fact, Bob doesn't have to just send this message to Alex. Bob can post this on the internet for everyone to see. Bob says, okay, if you want to send me a message that you don't want other people to read, here's what you do. So I'm giving you publicly the method or the key to the crypto system. And the method is as follows. I'm going to So Bob sends a a number, an integer, n, and another integer, e. E stands for, this is the encryption method. And how do you encrypt? So, oh, and I should say, first of all, every message is a number. I mean, you don't need to send words. You can write every word as a number. Like you can say A is 0, 1, B is 0, 2, C is 0, 3, and so forth. Z is 26. There are 26 letters in the English alphabet. So if you have any word like cat, you just write it as a number. C is 03. A is 01. What is T? Let's see. A, B, C, D, E, M. Let's see. N is the 14th. N, O, P, Q, R, S, T. 14, 15, 16, 17, 18, 19. So if I did this right, T is 20. So 03, 01, 20, that's the word cat. So, so you just take your message in words and you write it as a number. And anyone can say, okay, 03, 01, 20, CAT. So you're only sending numbers. You're not sending words. I mean, there's no reason to. So your message M that Alice wants to send is a number. And we compute M to the power E mod N. Okay. So what does this mean? You take M, you raise it to the power E, you look at the congruence mod N, and you send that number. Right? Like, suppose N were 15 and E were 7, and the message M is 2. So 2 to the 7th mod 15. You see, 2 to the 7th, I think, is 128 mod 15, which is 13 mod 15. So if your plain text message is 2, when you encrypt it, you get the number 13, and you send the number 13 to Bob. And Bob has a way, so let me just say, you take two primes. I'm making really very trivial stuff. P equals 3, Q equals 5, N is PQ is 15. And I let E be equal to 7. So this is the public key crypto system. It's N equal 15, E equals 7. So Bob announces to the world, N is 15, E equals 7. If you want to send the message M, which is your plain text, choose C to be congruent to M to the E mod N, or M to the 7th mod 15. So if M is 2, if that's the message you want to send, then 2 to the 7th is congruent to 13 mod 15. So your ciphertext is 13. So here's Alice, here's Bob. Alice's secret message is 2, which he converts into the number C equal to 13, and that's what she transmits. So Bob gets 13. Now, how does Bob decipher this message? Well, suppose we let D be some solution of the congruence ED congruent to 1. Now, this will seem sort of strange because I'm not justifying this. ED congruent to 1 mod 8. Let's see, what is E? E was 7. So 7D congruent to 1 mod 8. I can let D equal 7. So Bob can take 13 and try to compute what is 13 to the 7th mod 15. Let's see, let's do that. So 13 to the 7th is minus 2 to the 7th is minus 128. This is all mod 15. Minus 128 is that right? Mod 15. Let me just double check that. I mean, none of this is going to make sense, but at least I want it to work. So Bob chooses the primes P and Q, multiplies them and gets 15. And he chooses the number E that is relatively prime to choose the number E equal to 7. And he transmits the numbers 15 and 7. And the encryption method is, if your message is M, take M to the power E mod N. So M to the 7th mod 15. So if M is 2, then 2 to the 7th mod 15. 2 to the 7th is 128. Oh, I think I did this wrong. 128 mod 15. 128 mod 15 is, let's see, 7 times 15 is 105. So this is 8 times 15 is 120. This is 8 mod 15. So that's the ciphertext. So the message that Alice transmits to Bob is 8. And Bob computes 8 to the 7th mod 15. Let's see what that is. A to the 7th, I have to compute this mod 15. So A to the 7th, let me see if I can write 7 is 1 plus 2 plus 4. This is A to the first power, A to the second power, A to the fourth power. So this is 8. 8 squared is 64, which is 4 mod 15. A to the fourth is a squared squared, which is 16, mod 15, which is 1. So this is 32, which is 2. So a to the seventh mod 15 is 2. And I recovered the secret message. Okay. Let me go through this again more systematically, so there's an idea about how it works. So we've been looking at congruences, and one reason we've been looking at congruences is because they are absolutely central in cryptography. So we had proved what is called Fermat's little theorem, which says that if P is a prime number and P does not divide A and P are relatively prime, or the GCD of P and A is 1, then A to the power P minus 1 is congruent to 1 mod P. Now, I want to extend this. There's a two congruences modulo a product of two primes. So let P and Q be primes, distinct primes, odd primes. We don't need P equal 2. And let G be the greatest common divisor of P minus 1 and Q minus 1. And let the GCD of A and PQ be equal to 1. So P doesn't divide A, Q doesn't divide A. So we know that A to the P minus 1 is congruent to 1 mod P, and A to the Q minus 1 is congruent to 1 mod Q by Fermat's little theorem. Suppose you look at A to the P minus 1 times Q minus 1 over G. G is the greatest common divisor of P minus 1 and Q minus 1. So this is equal to A to the P minus 1 raised to the power Q minus 1 over G. This is an integer because G divides Q minus 1. And G divides Q minus 1. What is this congruent to mod P? A to the P minus 1 is congruent to 1 mod P, so this is 1 to the Q minus 1 over G, which is 1. So A to the P minus 1, Q minus 1 over G, P divides A to the P minus 1, Q minus 1 over G minus 1. That's the definition of congruence. This is congruent to this mod P if the difference is divisible by P. And if I also look at this mod Q, I can write this as A, P minus 1, Q minus 1 over G is the same as A to the Q minus 1 raised to the P minus 1 over G power mod Q. This is 1 to the P minus 1 over G, which is 1. So P divides this number minus 1, and Q divides it. And P and Q are distinct primes. So if two different primes divide a number, the product does. So PQ divides A to the P minus 1, Q minus 1 over G minus 1. So A to the P minus 1, Q minus 1 over G is congruent to 1 mod PQ. So let's look at chapter 3, which is in course materials. And this should be exactly one of the theorems. Let's see. Yeah. So this is in chapter 3. This is theorem 3.1. So we have PQ distinct primes. G is the greatest common divisor of P minus 1 and Q minus 1. And if A and PQ, if the GCD of A and PQ is 1, then A to the power P minus 1, Q minus 1 over G is congruent to 1 mod PQ. Now, let's look at some other simple results. Simple after you know them. Suppose we just take 1 prime P. And we take an integer E where the GCD, the greatest common divisor of E and P minus 1 is 1. So if E and P minus 1 are relatively prime, then there exists an integer D such that D times E is congruent to 1 mod P minus 1. The units mod P minus 1, the invertible elements, are the numbers E relatively prime to P minus 1. That means those are the numbers E for which you can solve this congruence, for which there exists an integer D if DE is congruent to 1 mod P. Suppose X to the E is congruent to C mod P. So suppose X is the solution of this congruence, and you want to find X. So this is like you're trying to find the Eth root of C. And how can you do that? Well, if you take C to the power D, C is X to the E. That's X to the E to the power D. That's X to the D times E. If DE is congruent to 1 mod P minus 1, that means DE minus 1 is some multiple of P minus 1, where DE is 1 plus some multiple of P minus 1. So this is X to the 1 plus K P minus 1. This is all mod P. And X to this power is X to the first power times X to the K P minus 1. Let me just start this again, just to try and make it a little bit clearer. This is a proposition. You have a prime number P and a positive integer E, E greater than or equal to 1, which is relatively prime to P minus 1. So by our understanding of units with respect to congruences, if E is relatively prime to P minus 1, there's an integer D such that D times E is congruent to 1 mod p minus 1. So if dE is congruent to 1 mod p minus 1, that means dE minus 1 is a multiple of p minus 1. P minus 1 divides this. So dE is 1 plus k times p minus 1. Now, we suppose that x is a solution of this exponential congruence. X to the e is congruent to c mod p. So we know what e is, and we're told that x to the e is c, and we want to find x. So we have dE is 1 plus k times p minus 1, and x to the e is congruent to c mod p. We're given c, we want to find x. So suppose I take c and raise it to the power c times d. That is, yeah. So this is c. See, d times e is 1 plus k times p minus 1. This is c to the 1 plus k times p minus 1, which just by the rules of exponents is c times c to the k times p minus 1. But c to the p minus 1 is congruent to 1 mod p, if GCD of c and p are relatively prime. C is 0 mod p, everything is 0. So this is congruent to c times 1 to the k, or just congruent to c mod p. So c to the d, c to the de, this is c to the d to the e. So if you take c to the d and raise it to the power e, you get c. So x is c to the d. Again, let me, we have a message x. Think of this as cryptography. We have a message that we want to encrypt, x. And what we do is we take x, raise it to the power e, and reduce it mod p. So we have x, this is the plain text, and we raise it to the power e, and we get the number c, which is the ciphertext. So if this were the basis of a crypto system, you would give the world the prime number p and the exponent e, and say we encrypt a message x by taking x to the e, reducing it mod p, and sending the number c. So this is the ciphertext. And then we want to reverse this. The decryption process is, given c, how do you get back to x? And the answer is, we know p and we know e, choose d such that de is congruent to 1 mod p minus 1. We choose a number, we choose p, and we choose a number e, which is relatively prime to p minus 1. Choose d to solve this congruence, and then x is going to be c to the d mod p. So if you know p and e, you can solve this congruence for d, and knowing d, you can get x back. So this would be an example of an insecure, which means a bad crypto system. If you encrypt by raising your plain text to the power e mod p, it's easy to decrypt that. So this is not, and the public key, which you would send to everyone in this case, the public key would be the prime p and the encryption exponent e. And from this you can encrypt, but anyone could decrypt. So this is an insecure, bad crypto system. And the very simple, clever modification of this gives you the RSA crypto system, which is secure. Yeah. So let me state this now as part of this is a proposition. This is 3.4. So P and Q are distinct primes. E is a positive integer such that the GCD of E and P minus 1, Q minus 1 is 1. That is, you have the prime, you know the primes P and Q, subtract 1 from P, subtract 1 from Q, multiply them, and choose a number E that's relatively prime to P minus 1, Q minus 1. So there exists an integer D that solves the congruence DE congruent to 1 modulo P minus 1, Q minus 1. Suppose the integer x solves the congruence x to the e congruent to c mod pq. This would be an encryption method. You would tell the world what is pq, the product. You don't say what is p and what is q. You just give the product. You give the power e, and given a number x, you encrypt it by taking x to the e and reducing it mod pq. So this congruence has the unique solution that is given E, given C, how do you find X? X is congruent to C to the power D mod PQ. So for the proof, let's suppose the GCD of C and PQ is 1, then so DE congruent to 1 modulo P minus 1, Q minus 1 means that DE is 1 plus some multiple of P minus 1, Q minus 1. So x to the e or so. If I take x equals c to the d, c to the d to the e is c to the de is c to the 1 plus k p minus 1 q minus 1, which is c times c to the k p minus 1 q minus 1. But we just saw that c to the p minus 1 q minus 1 is congruent to 1 mod pq. So this is just 1. This is congruent to c mod pq. So x equals c to the d is one solution of this congruence. So if x to the e is congruent to c mod pq, then x is congruent to c to the d mod pq. Or at least this is one solution of the congruence. And if u is any other solution of x to, of x to the e congruent to c mod pq, what's unique then? This is the only solution, mod pq. Just leave it. So this is an encryption algorithm. The question is, how efficient is it? So if we let n equal pq and e to be an integer such that the greatest common divisor of e and p minus 1, q minus 1 is 1, then the encryption algorithm is x is sent to x to the e mod n. And you decipher this, decrypt, by computing d such that de is congruent to 1 mod p minus 1 q minus 1. And if you know p minus 1 q minus 1 and you know e, it's easy to find d. So must know p minus 1 q minus 1 given n, which is pq and e. How do you do this? How do you get p minus 1, q minus 1? Well, you might say it's easy. You have n, you factor it, you find p and q, then you know p minus 1, q minus 1, and you can find e. So you must factor n to compute e. And factoring is hard. That's the whole message that I am trying to convey here. So this is the RSA crypto system. RSA crypto system, which is a public, this is an example of a public key crypto system. So what is the setup? That P and Q be two large distinct primes. Thousands of digits, huge. Then E and C be integers. What is the problem you have to solve? Solve the congruence x to the E congruent to C mod n. In this crypto system, you tell the world n, which is P times Q. You tell the world E, you have a message x, raise x to the power E and reduce it mod n, and that's C. So if you know E, C, and n, find x. You have to solve this congruence for x. Now, this is easy for Bob. Bob knows P and Q. So Bob knows how to subtract. He knows P minus 1 and Q minus 1. And Bob, this is easy, solving a linear congruence, solves DE congruent to 1 mod P minus 1 and Q minus 1. And as soon as Bob solves this congruence for D, so then Bob gets x and C to the D mod n. Just does this calculation, Bob finds x. So this is easy for Bob. But it's hard for Eve. Eve knows n, which is PQ, but she does not know P and Q. So solving this congruence is easy if you're Bob, but hard for Eve. That's all it is. And you have to know some number theory to understand this. But this is the RSA crypto system, and it is extraordinarily powerful. Now, you can ask the following question. Is RSA truly, whatever that means, hard? And the answer is no one knows. Is it secure? Same answer, no one knows. Why does it seem to be hard? Why does it seem to be secure? It's because there seems to be no effective way, even if you know that a number n is a product of just two different prime numbers, to factor n to find the prime numbers. So no one knows because factoring seems to be hard. All that means is that billions of hours of computer time, human intellect time, artificial intelligence time have gone into trying to figure out how to factor a large number, and no one can do it fast enough to break the code. Which is why Amazon gets rich, because its encryption scheme, which is RSA, works. Let's look at a small numerical example. And in the text, this is in chapter 3, page 120. So Bob chooses two secret primes, P and Q. Bob, they are secret. Bob knows them and he doesn't tell anyone. Let's say he takes P equal to 1223 and Q equal to 1987. And then he computes P times Q, multiply 1223 times 1987. You can do this on your calculator or on your computer. You get 2,430,101. Bob chooses a public encryption exponent E, and let's say he picks the number 948,047. And you can check. You need a calculator or a computer, but you can check that the GCD of E and P minus 1, Q minus 1, which is the GCD of 948,047 and 2,430,101 is 1. These two numbers are relatively prime. And what Bob publishes to the world are the numbers N and E. 2,430,101 and 948,047. So this is the public key creation. This is what the world knows. N is 2,430,101, and E is 948,047. So then you have, how do you encrypt? So this is an example of RSA encryption in this case. Suppose Alice has the plain text, right? Your text, whatever it says in words, is converted to a number. M, this is her message, which is 1,070,777. So this number is between 1 and n. Right? This is a number between 1 and n. So how does Alice get the ciphertext? C, you take M, raise it to the power E mod n. So you take the number 1,070,777, raise it to the power 948,047. Okay. You don't want to do this by hand. But if you do it, and you get it, what this is congruent to is, it turns out, 1,473,513 modulo my n, 2,430,101. So this is the ciphertext. So Alice sends C equal to 1,473,513 to Bob. And Eve can intercept this, but what's she going to do with it? The plain text was this number. This is the ciphertext. How do you get from the ciphertext back to the plain text? How do you decrypt? Well, this is the RSA decryption. This is how you go backwards. Bob knows P and Q, and he knows E. So Bob solves the equation D times E congruent to 1 mod P minus 1 Q minus 1. That is D times E, 948,047 times D congruent to 1 mod P minus 1 Q minus 1. P minus 1 Q minus 1. 1222 times 1986. When you multiply them by hand if you're patient, by calculator if you are not, P minus 1 Q minus 1 is 2,426,892. And you get D is equal to 1,051,235. So you compute C to X is going to be C to the D mod N. So you have this number raised to this power reduced mod N, and you're done. But the reason this can be decrypted is Bob knows P minus 1 and Q minus 1, and so he knows their product. The reason Eve cannot break this code is she doesn't know P and Q. She just knows their product, and she cannot figure out, and her computers cannot figure out how to factor the number. Now, in this case, these numbers are pretty small, and they can be factored. Let me try something here. Let me see if I can share my screen with Maple. So if you've taken calculus at Lehman and you were lucky enough to learn Maple, that's good. So you should be seeing this Maple window. And in Bob's crypto system, P is equal to the prime (1223), and Q is equal to the prime 1987. So N is going to be P times Q. There it is, 243,010. And that's just a few million. That's the I factor. And there it is. So it's hard to do this by hand, but Maple does this in a microsecond. Because these are really, really, really small numbers. Let's do an experiment. I have no idea what a prime might be. I'm just here's the number. Is this prime? It is prime P. Well, oh, that's not prime. Maple says this is in fact. Yeah, I see factor. So let me change this a little bit. Stick it through. Still not a prime. No, how to find a prime? Huh. That's an easy prime, a big prime. Still not a prime. Make it easier. How to find a prime? Ah, so here we have a prime number. Okay, that's good. Try another. Which Q is Ah, there's the prime. So the green numbers. If I let n be q times q, that's n. Not certain, that's it. See if Maple can factor that. Oh, they did factor. Good for me. Okay. But even these primes are pretty small. In practice, you use primes with thousands of digits, and they're hard to find. There are companies that find them and sell them. You might say that's kind of a weird business, but there's actually a business that people make a lot of money from, using computers to find large prime numbers and sell them to companies for use in RSA public key crypto systems. Okay. So this is your assignment, if you like. Someone thought we were spending a lot of time proving theorems in mathematics, and where's the cryptography? And here's an example. This is where cryptography is done in a serious, commercially valuable way using these basic theorems from elementary number theory. I'll talk about this a little bit more tomorrow and have some homework problems that involve RSA, because this is definitely in the midterm next week. Okay. If there are any questions, I'm here, and I'll be back at 7 o'clock tonight, as I am almost every night, if you need some help. Bye.